Hello everyone, my name is Roy Jafari and I would like to welcome you to another video. In the last two videos, we started talking about decision trees and how we would go about making sure that the decision trees are not overfitted. In this video, we are going to look at a couple of examples, actually two examples, of actually implementing decision trees on datasets using R. So the outline of this video is very simple. We're going to look at two examples. We're going to look at example 1 and example 2. So example 1, this is the one example we've been doing the classification on in all of our videos. So we've got two independent attributes, right? So these are our independent attributes or our predictors, and we've got our dependent attribute or our target. So we want to try to predict target, which is of categorical nature, using the two independent attributes income and score. Alright, so let's try and do this in R and see how that would look like. Alright, so this is our R environment, and of course the first thing we need to do, like always, we have to install a few packages and also call those packages. These are the packages we're going to be needing to do decision tree. And R part is the one package that does the decision tree for us, and this is the package that creates the plot of the decision tree for us. Alright, so first we will read our df, which is, as we saw, the data that we saw together. We've got income, score, and default. And we also make sure that our default is known as our factor or our target. So making sure that this is always the case for classification algorithms in R. Once we do that, then we simply use the rpart function and we say, okay, we want to predict default based on income and score, and this is our data, and this is the method is class. So when we say it's class, it means that this is going to be a classification, and rpart is going to do this as classification. So pay attention here. Normally when I have, in the previous videos would do classification, I would separate the data into train set and the test set. The reason that I'm not doing that here is because there are times that we just need to look at the decision tree visual at the end to sort of see the patterns in the data, right? If our end goal is the descriptive, seeing what's happening in the data and finding the patterns, and if that's our end goal, we don't need to split the data. We can use the whole data to come to that one visualization we want to look at and extract the patterns for our use. So, imagine that that's what we are trying to do here. We are not trying to look at to use this for any predictions. We're just going to sort of see how the end result will look like. So I go ahead and run this, and I also can say the summary of it. And these are some of the stuff that we will look at in a minute. So let's look at the actual visualization of the decision tree or the decision tree visual, and we can see that the root test is score larger than or equal 790, which is the credit score if it's yes or no, and if it's yes, then we've got no default payment, and if it's yes, more often we have yes default payment. So one might ask question, is this a fully grown decision tree? And the answer is no, it's not a fully grown decision tree, and the reason is that R automatically prune the decision tree for you. And if we want to stop that from happening, we have to specify three parameters in this function. We have to specify CP complexity parameter as 0. This is something that R internally uses for pruning, and we can also sort of set this ourselves if we want to be the one who prunes the decision tree ourselves. But that's the sort of the way that R does it. And then we've got mean split, which is the minimum number of subset your data of the minimum number of a subset in your decision tree that can be splitted, right? So we put that as 2, so there is a split possible, and the mean bucket is the minimum number of data objects at the leaf node, which we put it as 1. So once we do all of this for any decision tree, we put these 3, then we will force our part to create a fully grown decision tree. So once we do that, now it's a fully grown decision tree, and you can see we have all pure nodes, right? So this is a pure node, this is a pure node, and this is a pure. So, like I said here, our goal, it wasn't to do any prediction. This was a very small data set. So our goal was here to sort of see the pattern in the data, and we can see nicely how the patterns in the data look like in this visual. So now let's go back and look at the second example. In this one example, we want to predict if a customer of a telecommunication company is going to churn or not. So we've got these independent attributes, and this is our dependent attribute. And we want to apply decision tree here and see what will happen. So let's get back to R, and this is that data set. So let's read this, and let's also call df here to sort of see the data. We can see that data is much larger. Right? And we've got 3,150 observational rows, right? And here again, we make sure that we put churn as factor, so our decision tree algorithm is not confused. And because we are trying to randomly split the data, let's make sure that the randomization is in control. So we use set seed as 1, and we randomly create indexes to split our train and test set by 70%. So we're going to have 70% of the data as a train set and 30% as a test set. So that's how we do that. And now here we say this is our model. We want to predict churn based on all of the other attributes in the data, right? And I'm using this train set, and I want to look at the fully grown tree, right? So I'm setting these as CP0, min split 2, and mean bucket 1. So once I run this, now I will see that there are a lot of stuff happening here. There are a lot of calculations behind the scene, and this is so large that I don't get to see everything here. I mean, there are stuff on top that sort of like exceeds the limits of the count console. But anyway, let's look at the end result. And when we look at the end result, this is pretty large, and the reason is we are sort of like forcing forcing this function R part to sort of like go all the way to the pure leaf nodes. And we didn't need to do that. I mean, we just did this as an example, and we can actually, for the most part, trust the tuning of R, right? We could take the tuning, we could take the pruning of decision tree in our own hands, but decision tree R part has a pretty nice tuning mechanism and pruning mechanism. If it's not a part of a research that you're trying to do, sometimes that might be a question of if I put the CP as a different value, what would happen to my end result? If this is not what you're trying to do, which is not, of course, during this course, then you can just trust the R part and let it decide all of those parameters. So let's just do that, and remove the CP0, min split 2, and mean bucket 1, and let's just run it and see what will happen. And this time we have a much smaller tree, right? So this is a much smaller tree, and it kind of sort of like, it's not really obvious here. So one thing we can do, we can save it as PDF, and open the file wherever you're doing all of your codes and your data from, it's going to be saved there. All right, so as you can see, this is what the final tree looks like, and you can sort of see it and access it this way, right? And so one of the ways we could have done the pruning ourselves, let me go back to here. The pruning happens by looking at the X error, which is the amount of error on the cross-validation that the R part does on your data. And when the the number of splits keep going up, based on what is the best split in the data, and once the X error start to decrease, the moment it start to increase again, so it start decreasing first, so it decrease, and once it start to increase again, and not again, increase for the first time, then that's the time that the R says, okay, this is where I'm going to stop. And that's this complexity parameter that I was telling you about. One thing you could do is to let the decision tree fully grow the tree, the R part, and then come back and choose this for yourself, which would result to the same conclusion. But anyway, let's use this final decision tree for our prediction, right? So now we want to predict the test set, we want to predict the class, and once we do this, once we run this line of code and then of course create the confusion matrix, we see that our accuracy here is 93%, and our sensitivity, which is the positive rate, which is correct prediction of the churn cases, is 77%, but correct prediction of the non-churn cases is 96%. And if you look at the confusion matrix here, we do see that we're doing pretty nice on 0, 0, but out of all of the ones, we have 34 of them that we were not able to predict. So would we be able to do better if we sort of like had a different cutoff point? So let's experiment that, right? So first thing we need to do is to get the probability values instead of the final class. So when we do that, now we have the probability values. This is going to have the probability values, and we use the cutoff point 0.1 or 0.10, right? And this is 0.1. And be using that cutoff point, now we have a prediction based on this. Now we use that prediction for our confusion matrix, and we do see that we managed to improve the sensitivity at the cost of specificity, as we would have expected this to happen. And lastly, we could also create our ROC based on the test set churn value and the probability values, and this is going to be our ROC, how it looks like, and we can also calculate the AUC for it, which is 0.9113. All right, so in this video, in a summary of this video, we looked at two examples of decision tree, two different data sets, and we applied decision trees for them, and we saw how decision tree, how R can help us with implementing decision tree, and what are the ways we can receive benefit from doing decision trees in R. All right, until the next video.